Alright, so yesterday I explained the basic mechanism for Infra-Bayesian Haggling. So I wanted to give you some more, some more interesting points about that. So first, we said that there's this. So let's take for a moment the prisoner's dilemma as a concrete example. Okay. So in the prisoner's dilemma, we have two strategies. Corporate, right? We have beta matrix is corporate effect, corporate effect, and let's say if both cooperate and it's 2, and if one cooperates and the other defects, then the defector gets 3 and the cooperator 0, and if both defect, we get 1. Okay, so here it's 1, 2, 3, 1, 2, 3. So we have the exploitation outcomes here, and the defect outcome here, and the corporate here. So we get this quadrangle shape. Okay, and now notice that here, any player can guarantee getting this one defect, right? So 1 is like the max impair in this case. So in terms of Infra-Bayesian Haggling, in principle, they are going to both start out trying to exploit the other player. Right, so they start up here, and then they go down. Okay, but go down half. So in principle, one case is when there is more or less perfect symmetry between the two algorithms, and the only difference is because they are randomly choosing different hypotheses. But on average, for in the large scale limit, they still kind of go down at the same rate. So they're expected to go somewhere, they hit this boundary somewhere very close to here. So the outcome is just cooperative fault. More generally, they don't have to be symmetric, right? They could have somewhat different priors. There's simplistic priors, unique, which is different ETFs. The other details in the algorithm are different, even though the overall kind of type of algorithm is similar. So, or they just have different values of k, right? So, maybe one remark about this k number. So remember that we had this kind of hypothesis class, and we said that we kind of got it off by taking only the RGBs that have some particular complexity or particular number of states. But another way to think about it is if we just take the entire thing, right? But our learning algorithm is not any time. So it explicitly depends on the time discount gamma. And then in the learning algorithm, we let k depend on gamma in some way that goes to infinity if gamma goes to 1. So such an algorithm is a valid learning algorithm, a valid non-anytime algorithm for this entire class. Right? Not just for this small class, but for this entire class. What happens if you want the algorithm anytime, where this complicates things, and I'll say some remarks about it later. But this is maybe the natural way to think about it, is we have learning algorithms with this hypothesis class, which are not any. So if those things are, so if we have some asymmetry, then we can go out on some asymmetric trajectory and hit the boundary here, for example. Right? So what does it mean to be here, it means that like this player plays some mixture of cooperate and defect, whereas this player plays cooperate. So like part of the time, the outcome is a mixture of cooperate, but cooperate defect. So this player gets exploited some of the time, but it's not getting so exploited that it's worse than defect effect. It's still better. It's still doing better off than defect effect. So this is like another possible outcome. Right? So this kind of so this is like the Pareto frontier essentially. Probably. So they could hit this Pareto frontier at any point. But what happens if they go past this point altogether? Right? What happens if the pace in which they lower their payoff requirements goes here? Well, I mean, you could continue it and get somewhere here, but this is not actually the thing that happens, because once you get to this line here, this engine is no longer going to ever lower its like demand value. Why? Because even for any RDP it has, the maximum has to be at least 1. The value of any hypothesis, literally any hypothesis in the class, is at least 1. So it's never going to go below 1. Instead, once they both went all the way here, this player is saying, okay, I falsified all the hypotheses which guarantee greater than 1. So 1 is the best I could get. So it just, it could at this point just start. At this point it can just start playing the most defensive hypothesis. And technically, it's still going to have some selection of hypotheses which all guarantee 1, under which it's going to choose things randomly, and sometimes they will be falsified, right? But it's like so it is actually possible that while it's falsifying various hypotheses, this other agent goes here, and then they will eventually converge somewhere here. But it's also possible that it will just choose some hypothesis which cannot be falsified, which is the hypothesis top. Right? There's like the top hypothesis, which is just like any hypothesis whose kernel B maps any state to just the entire O. So any hypothesis that has this property, if it gets chosen at some point, then it's never going to get falsified. And then this means that this player just commits to playing defect, because it's such a hypothesis defect as the always is. And the other player is going to just keep going down here until eventually it also reaches 1 and plays defect 2. So in this case, the outcome is just defect. So yeah. So we see that defect effect is also a possible outcome. Not everything is like always rosy, but there is a certain sense in which it's an atypical outcome. What I mean by that is we've seen that if the agents are symmetric, we get cooperate. If they're just kind of somewhat asymmetric, then we get something like this. And in order to have this outcome, there needs to be some relatively strong asymmetry between like the primes of those agents. So this theory doesn't guarantee suppression cooperation, but it's kind of at least gives it a sort of place of honor as a relatively typical outcome of this game. So what happens in more general games? So we always like have the same principle. In more general games, we have again two types of outcomes. Either like here, we get something on the Pareto frontier, on Pareto frontier above maximum. And the second option is the option analogous to this. What is the option analogous to this? But it might be not obvious just from this example what is actually happening. So what actually happened here is that one of the players just reached a point of giving up, and then like it's playing its maximum, right? So player one is playing a maximum strategy.
So does this mean that as player one is increasing k, every time k increases, all the password hypotheses with a bigger k are already falsified?
I mean, it's not increasing k. It's just if at the born at the beginning of time, it receives some gamma and it chooses some gamma k according to this gamma once and for all. That's what it means for it to be non-anytime.
Okay. So for any time, it's because I can also imagine a learning where the players increase k.
Yeah. So this is an so if you wanted to have an anytime algorithm, we would have to kind of increase this k over time, and then there would be new hypotheses coming in, and then like it's less clear what's happening. So I will get back to this case again. So here player one is playing the maximum strategy. What is player two doing? So in this example it's not clear because it looks symmetric, they're both doing the same. But in general it's actually not symmetric. What would be like a good example game to show the asymmetry? I don't know, we can like think of an example now. But you see that what happens here is that player one at some point is committed to playing a particular maximum strategy. At this point, player two might actually, at this point, player one kind of becomes realizable in some sense because it's kind of it's like typically following some simple trajectory, like just cycling through some steps. So player two, and at this point, is typically going to play some best response to this. It's playing the best response. Yeah, so is it guaranteed? I think it's guaranteed, but actually, I'm not, suddenly I'm not would be sure it's guaranteed because it kind of depends how much is lowered in payoff at this point, but I think that since it's still above this point, the best response still has to be there, right? Because the payoff of the best response cannot be higher than this, I don't think. The payoff of the best response cannot be higher than this because this is like the cooperative payoff. So it has to be, so the best response, So the best response payoff is somewhere on this, for general games, not for this game, but in general, it has to be somewhere in this interval. So this player will always hit this point. So this seems to be like the only two possibilities in two players. So what happens if there's more than two players? So there's, Yeah, so this is kind of the basic picture, but there's a lot of interesting variables. Like what happens if there's more than 2 players? What happens with anytime algorithms? And what happens? So this is kind of repeated game. Can we also say something like one shot? So all of those questions are not completely clear, but I want to give you some sense that there's some interesting stuff going on. What happens if there's more than 2 players? So we still have this basic dynamics, right? Where you start from some level of, so now it's harder to draw the pictures, but like, now maybe there's 3 players, so there's some 3-dimensional things, so they start from some point and then kind of go down. And there's like some surface, which is like there's some convex shape, which is the possible payoff of the game. But now, instead of only 2 possibilities, there is a whole large combinatorial set of possibilities. Why? Because, so what's the mechanism here, right? Either they kind of both agree, in some sense, on doing something, or one of them just gives up and does something unilaterally, and then the second responds to that. So in the n-player case, we can also have coalitions. So suppose that we have like a game with 6 players, and we look at some subset, for example, those 4 players. So those 4 players, they have a particular payoffs that they can achieve unilaterally, right? So there's some interesting. So if like P is the set of players, then for any subset A of players, there is some set, which we can denote by let's say UA, some subset of RA, which is those pair vectors this group can achieve unilaterally. So this would be some kind of a convex. So we can think of it as like a convex downwards closed set. Downwards closed, and also topologically closed set. Right, so what is this set? It's like the set of all pair vectors, such that there is some strategy for those players which guarantees that each of them gets at least as much as, right, let's write it this formally. So like, UA is the set of all vectors, and V is RA, such that, there is some kind of joint strategy. So what is the inference to joint strategy? Things like there is some kind of, let's call it alpha, right, in delta of like the product over I in A of A step choice. You can also have the actions which are also A. Okay, so not A. So let it be C for coalition. Right, so we have like things like that, such that, like for any like beta, the opposition plays, minus C, like and for any I C, the expected payoff of alpha times beta of the reward of I is going to be greater or equal than C R. Right. So So here there's also sort of assumptions, and it kind of gets technical because, or it gets interesting maybe actually, because here I'm kind of saying that those players, they cannot predict the way those players randomize. But is this actually the case? This kind of depends on the learning algorithm. So you know, the way we did it before, like the way the players kind of generate certain mixed outcomes is by just moving it some cycle. So this cycle is kind of predictable from the perspective of the other players. So here they should be able to do something somewhat better than this because they can kind of respond to the particular random bits. Instead of, so we could like have an alternative version where instead of this thing, we have beta, let beta be a kernel from this to, over C. Because the version of the distinction which works like this. On the other hand, ostensibly with more realistic agents, so this probably is not going to work with this chart, with this simple algorithm I presented, but arguably with more realistic agents, any coalition could find a way to like do some kind of a cryptographic pseudo-random that would be safe against the opposition. And therefore maybe ultimately this definition is slightly more relevant. So every coalition has this kind of UC, and now what happens is that we have this kind of vector of, we have some vector of how much each player demands. It's kind of going down, and once its projection in coalition hits this kind of UC set, then this coalition can locks into playing this corresponding strategy. And from now on, everyone else are sort of best responding to them. So what we ultimately get is some kind of a hierarchy where those are playing something unilateral, those are playing, for example, something that's best responding to this, but is unilateral with respect to those, and those are playing something which is best responding to this and cooperating with each other. So like the possible equilibria are this kind of hierarchies, like in coalition hierarchy.
It's always a tree or what's it?
I think it's just linear sequence.
Actually.
Because it's like, if you look at the Haggling process, then at every particular moment there's a new coalition forms. So there's some coalition that forms first, second, third.
They cannot form on the same step, or
I mean, if it's on the same step, then it's. I mean, maybe there's some very low probability thing that could happen, but typically.
If they form on the same step,
I
you
know,
can just treat them as one coalition. Or
yes, I think. I know that. I mean, there's all sorts of things that can happen with probability 0, right? I mean, this is all analysis is like for things that happen with probability that approaches 1 is k equals 2 things. Right? So there can be all sorts of weird accidents that prevent things from going that way, but that's not just the thing that happens with probability 1 is k equals 2. Whereas as gamma goes to 1. But by the way, what is gamma? We can also play with this because maybe each player has its own gamma, but we still assume that all of them can be gamma. So it's probably going to work as long as all of the gammas are going to 1. I think you still get this kind of. So this thing, it now no longer guarantees Pareto efficiency, even when everything is symmetric, it still doesn't guarantee Pareto efficiency. So in the 2-player case, if the agents are symmetric, you get Pareto efficient outcome. Here, it's not necessarily the case. Why? So example, the cake splitting game. So we have like 3 agents, and they're splitting the cake, but any 2 can overpower the third and take the cake to themselves. Right, so we have like players, so the players have like 1, 2, 3, and each player strategy is with whom they want to form a coalition. So AI's strategy is the set 1, 2, 3 minus I, let's say. And then, like, if 2 decide to coalition with each other, then they get half the cake, and this player gets 0. If they all kind of do a cycle, nobody coalitions with anyone, then they all get 1/3. Okay. So in this game, so they all start with so I guess they all start with 1/2, with 1/2, 1/2, 1/2. And now they are doing the coordination game, and in the coordination game, randomly, 2 of them will succeed to find the strategy of locking D on each other and cutting out the third one. So randomly, we get an outcome 1/2, 1/2, 0. Okay, actually the way I described it so far, it's not bad, because you could say that in a perfect symmetry, there is a probability 1/3 for every pair to form, and therefore on average the pairs are going to be like, so sorry, this is not yet an example of something not Pareto efficient. Let's still move on. So far it's still Pareto efficient, but now suppose that this outcome is actually not 1/2, 1/2, but 1/2 minus epsilon, 1/2 minus epsilon. Okay. So now, what happens? They start they start already with 1/2 minus epsilon, and they're randomly locked in. So on average, if this is like random, what's the payoff of what's the payoff, average payoff for the player? So it's going to be like with probability 2/3, 1/2 minus epsilon, plus with probability 1/3, 0. So this is like 1/3 minus 2/3 epsilon. So instead, you could have played this and got 1/3 all of them. So now it's not very efficient on average. I mean, okay, but now, so now on average it's not Pareto efficient, but you could still argue that at least this outcome in itself is Pareto efficient, right? But there's an example which is even worse, where you don't have even this, where even like the outcomes that you get, like not an average, but like the actual outcomes together, also not Pareto efficient. So we have again 3 players, okay, and we look at the payoffs, right? So each player has a payoff between 1 and 0. Each player has a payoff between 1 and 0. But let's say the outcome 1 is unrealistic, so there's no way to guarantee it without like exploiting the other player, and so since the way you agree to, for example. But there is some way for let's say that there is some way for the players. No, actually, it could be symmetric. As we said, there is some way for the players to agree on an outcome of 2/3, 2/3, 1/3. Okay, but there is also, and this requires the cooperation of all three. But there is also an outcome that allows those players to get 1/2, 1/2, and it is unilateral. And this player unilaterally, it can only just go. That's the maximum one is 0. Okay. So what happens? It could actually be symmetric. It could actually have, like, for any two players the same structure. So now what happens? So they start here, they go down. So when they are all on this level, they don't find this outcome because this player is not going to agree to an outcome that's only gives them 1/3. So they keep going down until they reach here. And here, those two lock in, or some two lock in symmetry. And like the first player goes all the way down to 0. So the ultimate outcome is 1/2, 1/2, 0, which is manifestly worse than, like, Pareto worse than, 2/3, 2/3, 1/3. But this 2/3, 1/3 is kind of, they cannot appreciate. So here specifically in the case when everything is symmetric, the outcome is not very efficient. But I think it's still kind of, so the theory is maybe kind of not as optimistic about coordination as you can think so far. We'll see, there might be some way to do better. But I think it's already interesting that there is kind of some kind of a pretty fun theory of this different types of equilibrium we can resolve.